In this lecture, we will talk about work done during an adiabatic process for an ideal gas, which is chapter 4. So we'll wrap up chapter 4 and then we'll start chapter 5. On chapter 5, we'll talk about the consequences of the first law of thermodynamics. So let's talk about the work done during an adiabatic process. We already talked about work done during isothermal process before. So we got the expression for specific heat capacity at constant volume before. So we got CV is equal to partial U partial T at constant V. So in this expression we see that U, which is the internal energy, is a function of T and V. Okay, so in other words, U is the function of T and V. So that means we can write the differential of U as the differentials of T and, or in terms of the differentials of T and V. So that is partial U partial T, okay, at constant V dt plus partial U partial V at constant T dV. Okay, and then we can use this expression for CV here. So du is equal to, this thing is CV dt plus partial U partial V T dV. Okay, and we know that internal energy of a gas depends on temperature only, which is shown by Gay-Lussac and Joule's experiment. And if we keep the temperature constant, then the change in internal energy would be zero. That means in terms of partial derivative, we can say that partial U partial V at constant temperature would be zero. Okay, keeping temperature constant, there won't be any change in internal energy. Okay, because U, we can say U is a function of internal energy only. When we keep the temperature constant, there is no change in internal energy. So that means we can write this expression as du is equal to CV dt, because this thing is zero. Let's call this equation 1. We also got an expression for Cp in terms of enthalpy. So Cp in terms of enthalpy is partial H partial P at constant, I meant to write partial T here. Partial H partial T at constant P is the specific heat capacity at constant pressure, and here H is function of T and P. Okay, in other words, H depends on T and P. So we can write differential of dH, or differential of H, as partial H partial T at constant P dt plus partial of H partial P at constant T dP, and dH is equal to, so this thing is Cp dt plus partial H partial P T dt dP. And for an ideal gas, Joule-Thomson experiment shows that this quantity would be zero. Okay, so we will show this in next chapter, chapter 5. So Joule-Thomson experiment shows partial H partial P at constant T is equal to 0 for an ideal gas. Okay, so by using that we can write our equation as dH is equal to Cp dt. Okay, so let's call that equation 2. Now we have first law of thermodynamics, which is the heat you supply to a system is used to increase or decrease the internal energy. Okay, if you are removing the heat, then the internal energy will be decreased. If you are adding the heat, internal energy would increase, and there would also be work, okay, either work done by the system or on the system, depending on whether you are supplying the heat or removing the heat. So now here we are dealing with adiabatic process. So for an adiabatic process, there is no heat entering or leaving the system, so dq is 0. So that means in this equation we have du is equal to negative pdv. Okay, so we can substitute this equation in our equation 1. So just a reminder, we got this equation in our equation 1. So Cv dt is equal to negative pdv. Okay, that's from equation 1. So let's put this pdv in this equation. So substitute 3 in 1, we get Cv dt is equal to just a second now, sorry, this is not equation 1, this is what we will get. Okay, so we got, let's see what we got for equation 1. Let me just go back and see what we have on equation 1. Oops. So we have du is equal to Cv dt. Okay. So Cv dt is du. So that means Cv dt would be negative pdv. Okay. Let's call that equation 4. Now let's define enthalpy. We already have the definition of enthalpy. Enthalpy is H is equal to, or defined as, U plus PV. In this case we are expressing the specific enthalpy. If you are talking about total enthalpy, then it would be capital U plus P capital V. Let's take differential on both sides. So dH is equal to du plus, use the product rule here, pdv plus vdp. Okay, so the reason we are doing here is we want to introduce both Cp and Cv in our adiabatic work. Okay, so we have du is du is pdv here, okay, in equation 3. So use that in this expression. So dH is equal to negative P dV. This is from equation 3, plus P dV plus V dP. We can cancel P dV minus P dV and plus P dV. And then we'll get dH is equal to VdP. Okay, and then we got on equation 2 we got the expression for dH. So let's go back and see that. So we already have an expression for dH. So let's see. So here is the expression for dH. dH is Cp dt in equation 2. So we can write that here. So dH is Cp dt is equal to Vdp. Okay, let's call that equation 5. Okay. So we got two expressions with Cp and Cv. One is this one, and we also got expression with Cv. So let's go back and see that. So that's this expression, equation 4. So let's divide equation 5 by equation 4. So divide 5 by 4. We get Cp dt over Cv dt is equal to Cp dt is Vdp and Cv dt is minus Pdv. Okay, cancel dt and dt, and then do the cross multiplication, or put like terms on one side and put all the like terms on the same sides. For the integration, we want to integrate to get the total quantity. So we know Cp over Cv is the ratio. Cp over Cv is gamma. So gamma dV over V is equal to dP over P. Now let's integrate on both sides. By the way, we also have negative sign here. So this gamma is constant, so we can just put it outside the integration. Let's say V goes from V1 to V2 and P goes from P1 to P2. So gamma, so integral of dV over V is natural log V from V1 to V2. The integral of dP over P is natural log P from P1 to P2. Okay, so gamma ln, so if I use integral, if I use the limits, then I get log V2 over V1 is equal to negative ln P2 over P1. Okay, so I can insert this inside the log. So when I do that, this becomes the power of this term inside the log. Okay, so it would be V2 over V1 power gamma is equal to negative. Now if I absorb this negative sign inside the log, then it will flip the numerator and denominator. So I can write ln P1 over P2, okay, by absorbing the negative sign. And if I flip this, you will have a negative sign outside here. So you can remove log and log on both sides. So that'll give us V2 V1 gamma is equal to P1 P2. Okay, so we can do the cross multiplication. P2 V2 gamma is equal to P1 V1 gamma. Okay, so this is the equation of state for adiabatic process. If you remember, we got the similar equation for isothermal process. In isothermal process, we had PV is equal to constant, or P1 V1 is equal to P2 V2 for isothermal process. So basically this is PV gamma is constant. Okay, here we have PV is constant. So this means here pressure is inversely proportional to 1 over V gamma. Here pressure is inversely proportional to 1 over V. Okay, so because gamma is usually greater than 1, that means the pressure decreases more rapidly in adiabatic process than in isothermal process. Okay, so if you plot PV graph for adiabatic process and isothermal process, what you will see is for isothermal process it decreases less rapidly than adiabatic process. So for adiabatic process it drops more rapidly. So this is for adiabatic process, and this is for isothermal. So later in the next chapter we'll deal with heat engines, where we'll have both adiabatic process and isothermal process, and then you will need to draw the curves for those processes. When you draw the curves, then you will need to draw the curves in different amounts of decay. Okay, so here our purpose is again to find work done during an adiabatic process. So let's define work. We already know work is integral of P dV. So work done during an adiabatic process. So here we will talk about specific work. Okay, so work, total work is P dV from, this is capital V, from V1 to V2, capital V1 to capital V2. But here we will talk about this specific work, which is work per unit mole. So here we would have small v, V1 to V2, and P small dV. Okay, so W is equal to integral from V1 to V2. Now we have expression for P from the equation of state for adiabatic process. So PV gamma is constant, so you can say P is equal to K over V gamma. So K over V gamma dV. Now K is constant, we can put it out. So the integral of V1 over V gamma is negative V negative gamma plus 1, negative gamma plus 1, and our limit is from V1 to V2. Now this K has both P and V. Okay, so that means we need to convert this to PV, because we want to apply the limit to that, just to simplify. So we can write this as P V gamma V negative gamma plus 1 over 1 minus gamma V1 to V2. So this V gamma and this V negative gamma cancel, and then we'll have P, we have V to the power 1 left, so that's V PV 1 minus gamma, and our limit is from V1 to V2. So work is so when you apply this limit to V, we also need to write different pressures. For V1 we'll have pressure P1, and for V2 we'll have pressure P2. Okay, pressure is not constant here. So for the upper limit, the pressure is P2, volume is V2, and for bottom limit we have pressure P1 and volume V1. Okay, applying the limits, and then we have on the denominator 1 minus gamma. Okay, so that's the expression for work done in an adiabatic process. And we see that in this expression, when V2 is greater than V1, because V is dominating in this case because of this gamma. So when V2 is greater than V1, this is the case when the gas is expanding. What we see is work is positive. When the work is positive, work is done by gas or system. Likewise, when V2 is less than V1, so final volume is less than initial volume, it's compression of gas. In this case, when V2 is less than V1, then we get work to be negative, and the negative work is work done on the system or on the gas. Okay, when you're compressing the gas, you do the work on the gas. When the gas is expanding, the gas does the work on the surrounding. So let's see an example that is presented in the textbook, where we are asked to find the work done during an adiabatic process. Okay, so here's an example of numerical problem. So we have a cylinder with a piston, movable piston. Okay, so this is movable piston, and this cylinder is covered with adiabatic wall, or you can say this is insulated. No heat can enter or escape the system, and it is filled with some gas. So this is some kind of monoatomic gas, and it's ideal. So ideal monoatomic gas. So we are given the initial pressure, initially the volume of the gas is 4 cubic meter, and when its volume is 4 cubic meter, its pressure is 8 atmospheres, and temperature is 400 Kelvin. Now you compress the gas. When you compress the gas, that volume would decrease, and we don't know what the volume is after you compress, and we also don't know the temperature. But when you compress, you change the pressure to 1 atmosphere. Sorry, you're not compressing here. I take it back. Actually, you are, in this case, you are either pulling it or it's expanding. Okay, the gas is expanding. So the pressure reduces to 1 atmosphere from 8 atmosphere. So this is the case of expansion. So we want to find these unknown quantities, as well as we want to find work. Here it's asking the total work, not the specific work. So total work done by the gas. Okay, in this case it's expanding, so the work is done by the gas. And we also want to find the change in internal energy of the system, of the gas. Okay. So when we deal with adiabatic process, we have this state equation of state. PV gamma is equal to, or P1 V1 gamma is equal to P2 V2 gamma. So gamma for monoatomic gas, okay, is 5/3 R. So we want to find V2 in this case. So rearrange this. V2 gamma is equal to P1 over P2 V1 gamma. So if I get rid of gamma on both sides, then I'll have here P1 over P2 1 over gamma and V1. So now let's plug in the numbers. So V1 is 4 cubic meter, 4. Pressure 1 is 8 atmospheres. Because we have the ratio of the pressure, so I don't need to convert atmosphere to Pascal. In other case, we need to convert atmosphere to Pascal, but here, since it's the ratio, so the conversion factor will cancel. So P2 is 1, and then gamma is 1 over 5/3, which is 3/5. So that will give us so we get V2 is equal to 13.9 cubic meter. Okay. Now we want to find temperature. For temperature, we can use ideal gas equation. So ideal gas equation is PV is equal to nRT. So for the initial state and final state, we can write P1 V1 is equal to nRT1, and for final state we can write P2 V2 is equal to nRT2. So divide these equations term by term, and then we get T2. Okay, so NR and NR are constants, so we can cancel that. So T2 would be P2 V2 over P1 V1 times T1. Okay, so plug in the numbers. P2 is 1, V2 is, we got that 13.9, and P1 is 8, V1 is 4 cubic meter, and T1 is 400 Kelvin. Okay. So in ideal gas equation, you need to express temperature in terms of Kelvin. Okay. If you're given Celsius, you will need to first convert it to Kelvin before you plug in the number. So T2 is equal to, you do the calculation, you get 174 Kelvin. So what we see here is when a gas expands, its temperature decreases. Okay. Because there is no heat involved, or you are not supplying any heat, that means it does the work at the cost of its internal energy. So there's decrease in internal energy, that's why there's decrease in temperature. So let's calculate the work here. So we have the expression for work. Work is 1 over 1 minus gamma P2 V2 minus P1 V1. Okay, so this one is all capital because we want to find the total work. So 1 over 1 minus 3/5 P1 or P2 is, now here we need to use pressure in Pascal. Okay, so for that I need to multiply pressure by this factor. So 1 Pascal is 1.03 times 10 to 5th Pascal. So pressure 2 is 1, so 1.01. Because we have pressure and pressure on both terms, so we can write this outside the parenthesis, factor that, take it outside the parenthesis. So that's pressure 2. Volume 2 is 13.9, and pressure 1 is 8 times that, and then take 10 to the 5th outside the parenthesis. V1 is also we have 1.03, that's 1.03, sorry. That's the pressure in terms of Pascal, and V1 is 4 cubic meter, and we have this times 10 to 5th. Okay, so when you do this calculation, you will get 2.74 times 10 to 6 joules. Okay, that's the work. Now we need to find internal energy. We have from the first law of thermodynamics, total heat supplied is equal to change in internal energy plus work done, and this is 0, so Q is 0. That means so we'll have delta U is equal to negative W. Again, here the work is done at the cost of internal energy. Okay, internal energy decreases when there is expansion. So negative of 274 times 10 to negative 6 joules is the change in internal energy. Negative sign implies that internal energy decreases. Or in other words, you can also say work is done by the system at the expense of its internal energy.